Assalamu alaikum. Today, I'll discuss two important studies. Oberoi et al.'s work on dynamics of graph isomorphism and Burgess et al.'s research on temporal graph analysis in sports. Now, both highlight how temporal dynamics drive deeper insights in algorithms and real-world strategies. Now, let's get started. Point number one. Oberoi et al. Addressed subgraph isomorphism in dynamic graphs, finding all subgraphs in a target graph that match a pattern graph. The key challenge is handling temporal changes, as previous methods often missed temporal consistency, which is vital for accurate real world applications. Point number two. Earlier approaches used an aggregated graph model combining edges from all time steps into one static graph, but this lost critical temporal details. Oberoi's snapshot-based model treated each time step as a separate graph while preserving the sequence, extending the VF3 algorithm with a tree structure to ensure temporal consistency. Point number three. Now, Oberoi's method was tested against Mackey's and temporal IRI algorithms on two data sets. It delivered competitive run times on large graphs and solved more instances with a set time limit, proving its superior accuracy and efficiency. Moving on to the explanation of the code.
So I successfully executed the code provided by Oberoi and the team. The algorithm effectively identified induced subgraphs within the dynamic target graphs as anticipated, utilizing the snapshot-based model and tree structure. The results align precisely with the claims presented in the paper. So now let's go over how the inputs were taken. So the inputs were basically a dynamic pattern graph represented as a sequence of graph snapshots such as adjacency and matrices evolving over time. A dynamic target graph also represented as a sequence of snapshots but encompassing a more extensive structure. Additionally, parameters including constraints like timeout limits or memory restrictions for the algorithm. And the output for this code was a detailed list of node matchings, highlighting the nodes in the target graph that corresponded to the pattern graph consistently across all snapshots. Performance metrics, which include runtime, the number of successfully identified matches, and memory consumption. This design offers the flexibility to process diverse datasets and the adaptability to accommodate various application scenarios effectively. Now moving on to Abhi.
I will discuss how Borges and colleges developed a temporal passing network model, TPNM, to analyze basketball player interactions by breaking each possession into discrete snapshots. The model generates graphlet profiles and transition profiles. The goal is to study how complexity in team behavior measured through entropy correlates with performance. Figure 3 shows the graphlet profiles for Argentina and Spain during the final of FIBA Basketball World Cup. Argentina heavily relied on simpler graphlets such as one no passes and 1-to-1 pass between players, indicating a straightforward passing style with limited interaction variety, while Spain demonstrated a richer variety of graphlets, including more complex patterns. The higher complexity in Spain's graphlet profile suggests an increased ability to adapt to defensive strategies and winning the game. Figure 4, transition and restricted transition profiles. This compares the transition profiles and restricted transition profiles. While Spain transition reveal a higher distribution across multiple graphs, Argentina's transition are concentrated on repetitive patterns, reflecting less adaptability. Spain maintains higher entropy even when self-transitions are removed, confirming their greater variability in switching between patterns. The study findings reinforce that higher entropy in passing patterns enables team to better exploit the property of degeneracy. By focusing on the temporal dynamics of these graphs, both papers emphasize the importance of preserving and analyzing temporal information to uncover deeper insights into complex systems. Thank you.